Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and today we're going to talk about one of my favorite subjects, the weather. Specifically, we're going to have a look at the atmosphere and whether or not we can use the ideal gas law to calculate pressures based on temperature. This is a common claim in the flat earth community that the pressure gradient is only due to the change in temperature as we go up. In other words, if we get colder, the pressure goes down. Let's go see if that actually works. Now let's go ahead and have a look at what's called the ideal gas law, and that is pressure times volume equals the number of moles of gas times the gas constant times the temperature in Kelvin. We can do some interesting things with this. So for example, if we have a set amount of gas at pressure 1 and volume 1, but we change the pressure to pressure 2, we're going to get a resulting volume 2. And because they're both equal to this middle term, we can create a gas law with that. In this case, this is Boyle's law. Now, the gas law that's in question with some of the flat earthers is called Gay-Lussac's law, and that relates pressure to temperature. So in other words, we just rewrite this a little bit, and we go to pressure 1 over temperature 1 equals NR divided by the volume, because we hold the volume steady, and that will equal pressure 2 over temperature 2. That's called Gay-Lussac's law. However, there's a couple of little problems here. First of all, is the atmosphere an ideal gas? Well, no it isn't, because an ideal gas has got 3 characteristics. And those characteristics are 1, the gas molecules are points with no volume. There are no intermolecular forces. In other words, the gas molecules don't interact with each other. And number 3, all collisions are elastic. That means that when one molecule bounces into another, all the energy is transferred to that second molecule. There's no cushion, there's no give. Now there's one more thing that you can add to this, and we'll just kind of stick it out over here. There's no forces acting on the gas. In other words, it's not being subjected to any sort of an external force. The only changes are due to changes in pressure, volume, and temperature. Now the Earth's atmosphere is pretty close to this, but it's not exact. There are some problems with that. Now we've got one more problem, and that is that if we have a flat Earth that's covered with a dome, that dome has a fixed volume. The dome doesn't move in and out and change the volume. So unfortunately, any gas law that involves a change in volume, like Boyle's law or Charles' law or the combined gas law, those all involve changes in volume. If you have a fixed volume under a dome, you can't change the volume, so they simply don't work. So that just leaves us with Gay-Lussac's law right here. Now, if Gay-Lussac's law actually reflects what really goes on in the atmosphere and is responsible for the pressure gradient, we should be able to take a particular temperature and predict a pressure from it. How would we do that? So standard temperature and pressure for the atmosphere when it comes to doing, say, aviation, is a temperature of 59 degrees Fahrenheit or 15 degrees Celsius. And a standard pressure, well, you can take your pick. We'll just call it 1 atmosphere. Okay? 1 atmosphere equals 29.92 inches of mercury. It equals 760 millimeters of mercury. It equals about 101 kilopascals, or about 101,000 pascals. You can use whatever unit you're comfortable with wherever you are. In Europe, they tend to use kilopascals. In the United States, we use inches of mercury. You can even use PSI if you wish. Just keep your units consistent throughout this entire equation. Well, let's go ahead and take some standard numbers here, and these are verifiable by direct measurements from airliners and barometers on the ground. So at sea level, the temperature is 15 degrees Celsius, which is about 288 Kelvin. The pressure, of course, is 1 atmosphere. Up at 10,000 meters, or about 35,000 feet, the temperature is minus 50 Celsius, which is about 223 Kelvin. Let's go ahead and do the math. So here we've set up the problem. We've got 1 atmosphere at 288 Kelvin equals the pressure at 10,000 meters over 223 Kelvin. We just rearrange a little bit and we get a final pressure. Now you can check my math, but this is about 0.77 atmospheres. Now, given sea level pressure is about 14.7 pounds per square inch, that means that we're on the order of 11.4 psi. That's a pretty high pressure. So why, when we measure the pressure at altitude, do we get a reading of about 3.5 psi, considerably less? That's because the atmosphere is not an ideal gas, and the temperature does not control the pressure gradient. It contributes to it, but it's not the main controller. What actually controls the pressure gradient is gravity. Now, some of you may know this, but I used to be a private pilot. In fact, I was an instrument-rated private pilot, and learning about the weather was a big part of my training. Let's go to some of the FAA manuals that I used to learn about the weather. Now, what we have here is called the FAQ, the Pilot's Handbook of Aeronautical Knowledge, and this is Chapter 12, Weather Theory. So this is the actual book that pilots use to learn about weather and aeronautical knowledge. Now, on the very first page, what do we have here? That must be that flat, non-rotating Earth that the flat earthers are talking about on FAA manuals all the time. Here we talk about the composition of the atmosphere. Oh, there's another flat, non-rotating Earth, talking about the limits of the troposphere, etc., etc., etc. Now, right here, we've got a very interesting point that it makes. If you look right here, you'll see that inside the troposphere, which is the lowest layer of the atmosphere where all the weather is, the temperature decreases at a rate of about 2 degrees Celsius for every 1,000 feet. Furthermore, the pressure drops about 1 inch of mercury for every 1,000 feet. Now, this is actually a pretty good rule of thumb. I've used this flying all the time. So when I go up to, say, 5,000 feet, I would expect my temperature to drop about 10 degrees Celsius and my pressure to drop about 5 inches of mercury. That has to do with my engine controls, manifold pressures, and things like that. And this is indeed pretty accurate based on the hundreds of flights that I've made. But it's only good for a few thousand feet. We need something a little bit better. But before we go into that, I'd like to go over a few other things that are in this FAA handbook that pilots use to train. Once again, we have the flat, non-rotating Earth that the flat earthers are always talking about. We have an entire section on Coriolis force and the importance of that in wind patterns. And one of the reasons that we have to learn all this stuff is that there's something called density altitude, which actually impacts our ability to take off from a runway of a certain length. So for example, on a hot summer day up in the mountains, the runway may simply not be long enough for you to be able to take off. And this is something that you have to be able to calculate. So this is important everyday stuff that pilots have to know. Now, to give us the data that we need to accurately predict weather, NOAA, the National Oceanographic and Atmospheric Administration, and the FAA put up weather balloons from airports all over the country a couple of times a day. And here's an example of what they call a skew-T graph, and this has the data from a weather balloon. This particular one was launched today, December 21st, from Green Bay, Wisconsin. Now, what you see on the left side here is the pressure in millibars. So you start off at 1,000 millibars at ground level, and it goes all the way up to 100. The red line is the actual temperature that is read as it goes up. They even track the balloon, as you can see here. So at each pressure altitude, it reads off a temperature. The green line is the dew point. And the margin of the tropopause is marked right here at 6915 meters. So what can we tell from this? Well, first of all, we can look at the distance between the dew line and the temperature. If this is really close, clouds are likely to form. And as they widen out in the upper atmosphere, the weather becomes rather clear. The other thing that we can do is we can take the pressure and read the temperature at that altitude. So 300 millibars is, roughly 9,200 meters. It's above the tropopause, as you can see. And if you follow this line down, you'll see that the temperature there is minus 50 Celsius. So again, this is airline height, and it's minus 50 Celsius. So is there some sort of a formula that we can use to calculate what the pressure should be at that height? Well, turns out there is. There's two of them, in fact. So basically what we do is we start off with the ideal gas law, and then we modify it based on two factors. One is going to be what are the actual intermolecular forces between the gas, because those can be measured in the lab. The other thing is what is the actual volume of the individual gas molecules, because we have to remove that from the total volume in the ideal gas laws. And then we have to take into account the effect of gravity. So what do we end up with? We end up with a couple of equations. I'm just going to give you two of them here because they're the ones that we're going to use. So if we want to know the pressure at a certain height, all we have to do is we have to take the pressure at the ground, we multiply it by the temperature at the height over the temperature at the ground, and then we take that up to an exponent. Well, what's the exponent? It's going to be G times R L. Now, G is gravity, the acceleration of gravity, 9.81 meters per second squared. R is the gas constant for dry atmosphere, and L is the lapse rate, which we measure with that weather balloon. Now, the interesting thing about this is these are all constants. So if we just take this little part right here and do the math for that, we get 5.255. So that exponent equals 5.255, and that depends on the gravitational attraction of the Earth, the characteristics of our atmosphere, and the lapse rate of the atmosphere. Now, if you guys would like, I'll go ahead and I'll put that value in for Mars and Venus because they're different. And I'll stick that in the comments. Just ask me about it, and I'll go ahead and respond. But let's go ahead and use this equation to figure out what the pressure would actually be at about 10,000 meters. So let's go ahead and do that. So PZ is going to be the pressure at the surface of Earth. We'll just use 14.7 psi. How's that sound? That's sea level pressure. We're going to multiply that by this fraction right here, this ratio. And this is the temperature at altitude, which we said was 223 Kelvin, over the temperature at the surface, which is 288. And then we're going to raise this whole mess to 5.255. Let's go ahead and see what that comes up as. And there you have it. I've done the math. That comes out to 3.83 psi, which is about 264 millibars. Recall that 9.2 kilometers up, 9,200 meters, is about 300 millibars. At 10,000 meters, it's going to be a little bit less, and that's what we're seeing here, 264 millibars. So what's the take-home message from this? Number one, the Gay-Lussac's law does not account for the pressure gradient in the atmosphere. Number two, the only way that we can accurately calculate what the pressure will be at any particular altitude is to take into account the effects of gravity. And there you have it. The pressure gradient in Earth's atmosphere is dependent upon the gravity of Earth. You can't figure it out unless you take into account the effect of gravity. It's just as simple as that. So guys, this is Bob the Science Guy. Thank you very much for stopping by. We're going to go ahead and put this to bed now and see you in the morning. Take care.